Hi, this is Alfozia Nihar from At Home Tuition. Welcome to our session today. The topic that we are going to discuss in our today's video is part 2 of the previous video, tangent lines and the rate of change. Let us start with rate of change. Here we are going to consider a function f of x that represents some quantity that varies as x varies. For instance, maybe f of x represents the amount of water in holding tank after x minutes, and maybe f of x is the distance traveled by a car after x hours. In both of these examples, we use x to represent time. Of course, x does not have to represent time, but it makes for examples that are easy to visualize. What we want to do here is to determine just how fast f of x is changing at some point. Say x is equal to a. This is called the instantaneous rate of change, or sometimes just rate of change of f of x at x is equal to a. As with the tangent line problem, the previous video, all that we are going to be able to do is at this point to estimate the rate of change. So let's continue with examples and think of f of x as something changing in time and x being the time measurement. Again, x does not have to represent time, but it will make the explanation little easier. While we can't compute the instantaneous rate of change at this point, we can find the average rate of change. So, to compute the average rate of change of f of x at x is equal to a. This is the formula to compute the average rate of change of f of x at x is equal to a. All we need to do is to choose another point, say x, and then average rate of change will be. Then to estimate the instantaneous rate of change at x is equal to a, all we need to do is to choose values of x, getting closer and closer to x is equal to a. Please don't forget to choose them on both the sides of x is equal to a. Hope you remember the example that we did in the part 1 video, tangent lines. Okay, and compute the values of average rate of change. We can then estimate the instantaneous rate of change from that. Okay, let me take an example. Here is the example. Suppose that the amount of air in a balloon after t hours is given by v of t, t cube minus 6 t square plus 35. We are supposed to estimate the instantaneous rate of change of the volume after 5 hours. Okay, the first thing that we need to do is to get a formula for the average rate of change of the volume. So in this case, the formula will be, I'm just implementing the average rate of change formula for this problem. This problem is dealing with volume. So this is what I have written for the function v of t. v of t minus v of 5 divided by t minus 5. Now you can replace v of t by the given function. You can replace v of t by t cube minus 6t square plus 35. And v of 5, you can just replace t by 5 in this equation and get a value. If you plug in 5 here, it is 5 cube minus 6, 5 square plus 35. So by doing the calculation, I'm getting v of 5 is equal to 10. If you simplify, you'll get that value 10. Okay, let's now plug in all these expression and the value. By simplification, we'll get the average rate of change now is t cube minus 6t square plus 25 over t minus 5. To estimate the instantaneous rate of change of the volume at t equal to 5, we just need to pick values of t that are getting closer and closer to t equal to 5. I'm going to make a table of values of t and the average rate of change for those values. It is just like assuming some x values and finding the corresponding y values by plugging in the assumed x values one by one in the equation. We are going to use this equation. I have assumed some values that are very closer to t equal to 5. I have started from 6 and ended up with 5.0001. 5.0001. Same way, you have to assume numbers both on right side as well as left side. So these are the numbers from left and the right. Now plug in these values one by one in the equation which is got in the previous step and find the corresponding average rate of change one by one. So the values that I got are, please have a glance over the average rate of change that I got for the assumed t values one by one. Please notice that the values are very closer to 15. All the numbers are approaching 15. So from the table, it looks like average rate of change is approaching 15. And so we can estimate that the instantaneous rate of change is 15 at this point. Am I right? So just what does this tell about the volume T equal to 5? Let's put some units on the answer from the above. This might help us to see what is happening to the volume at this point. Let's suppose that the units on the volume were in centimeter cube. I mean cubic centimeter. The units on the rate of change. I mean both average and instantaneous, or then cubic centimeter per hour. Am I right? We have estimated that at T equal to 5, the volume is changing at the rate of 15 cubic centimeter per hour. This means that at T equal to 5, the volume is changing in such a way that if the rate were constant, then an hour later there would be 15 cubic centimeters more air in the balloon than there was at T equal to 5. For all these problems, after finding the answer, you have to write the answer in terms of the words or the statement that they have used in the question. We need to be careful here, however. In reality, there probably won't be 15 cubic centimeter more air in the balloon after an hour. The rate at which the volume is changing is generally not constant. So, we can't make any real determination as to what the volume will be in another hour. What we can say is that the volume is increasing. Since the instantaneous rate of change is positive and we had rate of change for other values of t, we could compare the numbers and see if the rate of change is faster or slower at the points. For instance, when t equal to 4, please look at this table. The instantaneous rate of change is 0 cubic centimeter per hour. And t equal to 3, the instantaneous rate of change is minus 9. If you plug in 3 in your question, you can understand that. So it is 7.0 here, and t equal to 3, it will be negative 9. So we will leave it to you to check these rate of change. In fact, that would be a good exercise to see if you can build the table of values that will support our claims on these rate of change. Anyway, get back to the example at t equal to 4. The rate of change is 0, and so at this point in time the volume is not changing at all. That doesn't mean that it will not change in the future. It means that exactly at t equal to 4 the volume is not changing. Likewise, at t equal to 3 the volume is decreasing since the rate of change at that point is negative. So we can also say that regardless of the increasing or decreasing aspects of the rate of change, the volume of the balloon is changing faster at t equal to 5 than it is at t equal to 3, since 15 is larger than 9. Am I right? There are a lot more to talk about the rates of change. Okay, hope you're clear with this example. Now let's move on to the velocity problem. Let's briefly look at the velocity problem. Many calculus books will treat this as its own problem. We, however, like to think of this as a special case of the rate of change problem. In the velocity problem, we are given a position function of an object f of t that gives the position of an object at a time t. Then we have to compute the instantaneous velocity of the object. We just need to recall that the velocity is nothing more than the rate at which the position is changing. In other words, to estimate the instantaneous velocity, we would first compute the average velocity. Hope you all are familiar with average velocity? Yes, average velocity is nothing but change in position over time traveled. If you're going to write the same thing in symbolic form, you can write it as f of t minus f of a over the change in, the time travel t minus a. And then take values of t closer and closer to t equal to a. And then use these values to estimate the instantaneous rate. Are you clear with velocity problem now? Okay, let's have a glance over change of notation. There is one last thing that we need to do in this video before we move on. The main point of this video was to introduce us a couple of key concepts and ideas that we will see throughout the first portion of the video. So before we move into limits officially, let's go back and do a little work that will relate both. Okay, first notice that whether we wanted the tangent line, instantaneous rate of change or instantaneous velocity, each of this come down to using exactly the same formula. Am I right? Only the notations are different, but actually they are using the same formula. Change in something over time traveled. This should suggest that all three of the problems are then really the same problem. The concept that we discussed in our first video as well as this video, part 2. In fact, this is the case as well as we will see in the next video also. We are really working the same problem in each of these cases. The only difference is interpretation of the results. Am I right? In all of these problems, we wanted to determine what was happening at x is equal to a. At some point will be given in the question. To do this, we choose another value of x and plug that into the equation. For what we were doing here, that is probably most intuitive way of doing it. However, when we start looking at these problems as a single problem, will not be the best formula to work. What we will do instead is to first determine how far from x is equal to a. We want to move and then define a new point based on that decision. So, if we want to move a distance of h from x is equal to a, so if you're going to move h units, it would be a plus h. And if you're going to move, it will be on both the sides if you add or subtract h. That is the reason we repeatedly say that if you're going to assume some values, you have to look on both the sides, not just one side of the point. So as we saw in our examples, it is important to take values of x that are both sides of x is equal to a. This way of choosing new value of x will do this for us as we can see in the sketch. If x is greater than h is greater than 0, we will get a value of x that are to the right of x is equal to a. If h is less than 0, we will get a value left side of a. To get a new value of getting the second value of x, you can use this formula. This is the formula for general value of x, and on the surface it might seem that it is going to be an overly complicated way of dealing with this stuff. So it is just enough if you notice this formula. Actually, the concepts for rate of change, instantaneous rate of change, velocity problem, all are same thing, just a little bit change in the notation.